Welcome to lesson 4 of Puzzles to Exercise the Mind. In the beginning of this lesson, I'm going to go over solutions to several of the problems from lesson number 3. And then we'll proceed to do some other problems and exercises. Let's look at solutions to some of the card problems from the previous lesson, lesson number 3. First one was a full house. What's the probability of a full house was the problem that is solved. So we need 3 of one kind and 2 of another kind. So to get the 3 cards, first we need to pick the kind or the rank, whatever you want to call it, say 5s. So we would want 3 5s, and there's 13 ways of picking the rank. But then once you pick the rank or the kind, you have 4 cards, and you only need 3 of those. So it's 4, choose 3 or 4. So 4 times 13 or 52. And then once you've picked the kind, you have to pick, you have 12 choices for the kind of the 2 cards. So for example, you might have 3 5s and then 2 aces. And so there's 12 ways to pick the second kind because you already used up one here. And then out of the 4 cards of the kind you pick, say ace, there's 6 ways, 4 choose 2, 6 ways of picking 2 aces out of 4 or whatever particular rank you have for your second type here. So you get 12 times 6, and that's 72. Then you multiply 52 times 72. That gives you the total number of ways of getting a full house, 3,744. And then you divide by the total number of poker hands, which we computed in the last lesson. And when you divide, you get 0.00144, or about 0.144%. So it's pretty small. You may ask, well, what if you selected the 2 cards first and then the 3? You know, if you reverse the analysis. Well, if you do the 2 cards first, then you would have 13 choices here. So it would be 13 times 6. But then you would only have 12 choices for the 3 cards. So you'd have 12 times 4. But when you multiply all these together, you're still having the 12 and the 13 and the 4 choose 3, 4 choose 2 multiplied together. It's just the order's been mixed, but you get the same number here. So you would expect that because we're not concerned about order in this calculation. As I mentioned in the previous lesson, the poker hand doesn't depend on the order the cards are dealt to you. So straight flush is the second problem, and we can start with an ace, a 2, a 3, and the last card we can start with is a 10. That would be 10, jack, queen, king, and then ace. And we're not allowed to do wraparound, so you can't have like king, queen, ace, 2, 3. That's not allowed in poker. So there's only 10 choices for your starting rank. And then once you pick the starting rank, you need to pick the suit because it's a flush, meaning all the cards are of the same. They're all hearts, they're all diamonds or clubs or spades. So it's 10 times 4 is the total number of straight flushes, so very few. And you divide that 40 by the total number of poker hands, and you get this really small number here, or 0.001539%. You may ask, well, what about a royal flush? Well, a royal flush, there's only 4 ways to get that. And so you would have to divide this number. Instead of 40, it would just be 4. So you could divide this number by 10 and just add another 0 here, or 0 to the percentage. Then you'd have the probability of a royal flush, which is the highest hand you can get in poker. And you can see here the possibilities are really, really, really small to do that. We have one more poker problem to compute the probability, and that's for a straight, excluding straight flush. So from the previous problem, we know there's 10 ways of getting the starting rank for a straight. The difference here is that once you pick the starting rank, each card in your straight can be of a different suit. So for example, if we start with 3, 4, 5, 6, 7, Then the 3 could be a diamond, a heart, a club, or a spade, and so you have 4 choices there. And then for the 4, you have 4 choices. For the 5, 6, and the 7. So you have 4 choices each. So you have to multiply 4 times 4 times 4 times 4 times 4. So 5 times. So you get 4 to the 5th times 10. So this is the total number of straights, including straight flushes. But then we said we wanted to exclude those, so we have to subtract the 40 that we calculated on the previous slide. And then we have our 10 times 4 to the 5th minus 40 divided by the total number of poker hands. So it's 10,200 divided by 2,598,960. And we get 0.003925, or about that. It's not a repeating decimal here, so I just truncated it, or about 0.3925%. So again, pretty improbable, but more probable than some of the other hands we looked at. So there you have it. There's other probabilities we can compute, but I haven't done here. You may want to try the probability of getting 2 pairs that are not the same. So in other words, not 4 of a kind, or getting 1 pair and nothing else, and then getting sort of a bad hand, where you don't have any pairs or anything better than that. That's actually hard to compute, but if you're interested, I guess I'll throw those out as some additional poker problems to look at. Some of the solutions actually go beyond what we've talked about so far here. Okay, so let's look at the prisoner problem. Let's review what it was from the last lesson, and then we'll talk about how to solve it. If you recall, there was a warden of a prison. He made a special offer to 10 prisoners if they all succeeded in a given task. And the task had probability basically 1/2, unless there was some strategy, because what the problem was that each prisoner would go into a room, and there'd be 10 boxes, and each box would have a coin with the number of a prisoner on it. The prisoners were assigned numbers 1 to 10 also. So he would get 5 choices. Each prisoner would get 5 choices. If one of the boxes they opened had their number in it, that would be 1 success, and then that prisoner would leave and be taken somewhere else, so he couldn't communicate with the other prisoners. Second prisoner would go in, open 5 boxes, having no idea what the other prisoner had done, look at the numbers, and if his number came out, it would be success number 2, and then he would leave the room, and all the boxes would be closed, the room would be returned exactly as it was, and that would have to happen 10 times in a row. So as I mentioned in the last slide, that's like flipping a coin heads 10 times in a row. So it's probability 1/2 to the 10th power, which is pretty small. And the original problem I had seen had 100 prisoners, so they wanted to emphasize that it was almost impossible without some strategy to succeed. So let's see if we can figure a better way of doing this. I claim there was a way of getting a better than a 35% chance, just in the case of 10 of all prisoners being successful. So let's have a look at that. Okay, just to remind you here, I'm showing the picture from the problem itself. We'll talk about the solution on the next slide, but just to kind of emphasize what the room looks like. So the way they're arranged here isn't important. I just needed to fit them on the slide, but the coins are not visible when the box is closed, just to emphasize that. I just wanted to show you what it looked like when the boxes are open. The prisoner goes in, they open 5 boxes. So let's say prisoner number 6 goes in, and he decides to open these 3 boxes and these 2 down here. So he opens this, it's a 10, 7, 4, 5, and 3. So his number did not show up on any of these 5 boxes, so that was a loss. So regardless, even if that was a 10th prisoner and the first 9 were successful, this would be considered a failure, and then all 10 prisoners would remain and to serve the rest of their sentence. So in the case of number 6, he would have had to select box 10, but of course he didn't know where his number was, so he just picked 5 randomly, and in the example I give here, he lost out. So here's the solution, and again, just to remind you, the prisoners were allowed to discuss strategy before the process started, but once it started, there was no communication and no possibility of relaying any information back. Once the prisoner got done opening the boxes, he was allowed to, and leaving the room. The room was completely returned as it was for the second and then the third and so forth. So here's the strategy. Each prisoner starts with the box with his number on the box. So he doesn't know his number is going to be inside the box, but he still picks the number with his box. So let's say prisoner number 6 opens a box and it says 5. So he hasn't won there, but what he does is if there's a 5 in the box, he goes to box number 5 and he opens that box. And if that box says 3, he'll go to 3. So basically he's creating a loop. Eventually there's only 10 boxes there, right? So eventually the loop has to terminate and come back to the box that he opened first, because since there's only a finite number of boxes in the room. So that's the idea. You basically, each prisoner goes into the room, picks the box with his number on it, and then follows the number inside of the box to go to the next box and so forth. And if the loop is 5 or less, and he's only given 5 choices, right? If the loop is 5 or less, then he'll point the last box the last box he opens will point back to the first box, and whether that's in 1, 2, 3, up to 5, then he would win. So that's the trick. Let me illustrate it on the next slide with an actual picture. It might be a little easier to see what I'm explaining here. So we have an example here with prisoner number 3 using this strategy I mentioned. So prisoner number 3 goes into the room and he sees he's talked with all his colleagues when they've decided to use this strategy. So he opens box number 3 and there's a 4 in there. So he goes to box 4. That's why I have the pointer here. And he opens that box and that says 2. So he goes to box 2 and that says 7. And he opens, and that's, in other words, he goes to box 7. He opens box 7 and his number is in there. So he's only opened 1, 2, 3, 4 boxes. And of course, if his number is in that box, it's going to point back to where he started. So that completes the cycle. So the cycle is only of length 4. And he's won in this case. I just drew it down here on the to the right, so it's 3 to 4, and these are the box numbers: 3 to 4 to 2 to 7, and back to 3. So this is the cycle. And you may ask, well, how do you know that the prisoner, just by picking the box with his number, how do you know that that's eventually going to come back? That he's picked the box with his cycle on it, because it's always going to have, if he picks the box with his number on it, it's always going to be the cycle that eventually has his number on it. The only problem is it may take more than 5 boxes to get back. And again, the reason for that is, the reason that you always come back to the same box is that there's only a finite number of boxes, and these cycles need to complete. Because you can't go on indefinitely. And the way that completes is when you open the box with the number that was a coin that points back to the number of the box you started with. So there can be multiple cycles in here. This one here was of length 4. If prisoner 8 went in, then he would get lucky because that's of length 1, right? There's just one, the cycle of length 1, and then there's yet another cycle in here which I'll talk about. So we're kind of getting to where why this is a good solution, because as long as as long as all the cycles are of length 5 or less, every prisoner is going to win, because they'll pick a box with their number on it, and they'll come back to that box with from the box with their number inside in less than five or less steps, right? 5 or less boxes, and in which case you win. So we'll compute that probability. It comes a little over 35%. So let's go through a few more examples to kind of emphasize the approach here. On the previous slide, we saw a loop of size 4, and prisoner number 3 found his number in the box after only 4 tries. But what I want to add is that all the other prisoners, the other 3 prisoners whose number was one of the boxes in that loop, would also find their number in exactly 4 tries. So all 4 of them would have a success. Now I want to look at a different loop here, a different cycle. Let's start with prisoner number 1. He opens box 1, it has a 10 in it. So he goes to box 10 that has a 6 in it, which means he'll go to box 6 that has a 5 in it. He'll go to box 5 that has a 9 in it, and then he goes to box 1, which has his number. So prisoner number 1 is on a loop of size 5, and he'll find his number, as we saw, in exactly 5 tries. And that'll be a success since he's allowed to open 5 boxes. And in fact, any prisoner whose number is in this cycle would find their number in exactly 5 tries. So let's see, number 5 goes in and opens his box number 5 that has a 9 in it. So he goes to box 9. 9 has a 1 in it, he goes to box 1. 1 has a 10 in it, he goes into box 10. And 10 has a 6 in it, and he goes to box 6, and there's the 5. So no matter what number you pick in this cycle, the prisoner will come back to his number in exactly 5 steps, since the cycle is of length 5, and he will have a success. So all 5 prisoners with these numbers will have a success, and we know from the previous slide those other 4 prisoners will have a success in 4 tries, and there's just one other prisoner, number 8, but he's on a cycle of length 1, so he'll find his number right away. And since we have a cycle of length 4, a cycle of length 5, and a cycle of length 1, and they're all less than 5, that means all the prisoners will find their number in 5 or less tries, in which case they'll have an overall success and they'll be released. So very interesting. I think that this will work. What's even more interesting is you could up the number to 1,000 or 1,000,000 and allow the prisoners, and have 1,000 or 1,000,000 boxes, and allow the prisoners to open half the number of boxes, and the probability of success only goes down to a little bit less than 31%. In fact, as you go towards an infinite number of prisoners and an infinite number of boxes and allowing them to open half, the probability of success converges to 30.68, a little roughly, and we'll show that. Well, at least we'll talk about that in the next few slides. We're going to compute the probability of failure. So once we do that, then the probability that the prisoners are successful is 1 minus the probability of failure. To do that, we first count the number of ways of putting the 10 coins in the 10 boxes, and that's 10 factorial. It's 10 times 9 times 8 all the way down to 1. So that's the total number of combinations, but we're interested in which ones are cycles. So first we'll compute the number of 10 cycles. So that means you open box number 10, and that points you to 9, and 9 points you to 8, and so you don't get back to 10 until you've looped through all the numbers. So that would be a cycle of length 10. And if you recall from our discussion in lesson 3, the number of loops with n objects is n minus 1 factorial. So we have 10 objects here, and the number of loops or cycles would be 9 factorial. So the probability, if we randomly assign numbers to the 10 coins to the 10 boxes, the probability that you get a cycle of length 10 is 9 factorial, this number here, divided by the total number of permutations, 10 factorial, you get 1/10. So that's one way you can fail, but then you could get a loop of length 9 and then with one other number that's just cycling to itself. And then the number of ways of that happening is from the 10 numbers, pick the 9 that's in the loop, and then out of those 9 objects, there's 8 factorial ways of putting them in a cycle. And so you get 10, choose 9 as 10 times 8 factorial, and you divide that by the total number of permutations, and you get 1/9. So that's the second way that the prisoners could fail. Let's look at the case where you have a cycle of length 8, and you can see the pattern developing here, but let's actually compute it. So the number of ways of getting a cycle of length 8, first we pick 8 numbers out of the 10 to be in the loop, and then we have 8 objects, so there's 7 factorial ways of arranging those, but then we need to keep in mind for each one of these permutations of length 8, we have the other 2 numbers that are left over, and there's 2 factorial ways of arranging those. So they could be in single loops or just a loop amongst themselves. And so we get 2 factorial times 10 choose 8, which is 10 factorial over 2 factorial times 8 factorial times 7. The 2 factorials cancel out. The 8 factorial cancels into 10 factorial, just leaving 9 times 10 times the 7 factorial here, and then you divide all that by 10 factorial, and everything cancels out except for the 8 in the bottom here, so you get 1/8. And for a loop of length 7, the pattern continues here. You have to pick 7 out of 10 numbers to be in the loop. So it's 10 choose 7, and then there's 6 factorial ways of arranging those 7 objects in a loop, and then the other 3 that's not selected from the that's not part of the 7, there's 3 factorial ways of arranging those, and then you just expand this out, and the 3 factorials cancel, 7 factorial goes into 10 factorial, leaving 8, 9, 10. The 6 factorial carries over. Divide that by 10 factorial. The 6 factorial cancels everything down here except for 7, 8, 9, 10. And then the 8, 9, 10 cancels with that, leaving just the 1 over the 7 down here, and you get 1/7. I won't do the last one, but that's going to give you 1/6. So let's put all this together to figure out the probability that the prisoners will fail, and then we can subtract that from 1 to get the probability of success. So we're almost done. The probability of a loop greater than 5 is a loop of length 10, plus the probability of a loop of length 9, plus the probability of a loop of length 8, 7, and 6, so forth. We add those together, and amazingly, we don't get anywhere close to 1. We get 0.645635 approximately. The probability of success for all the prisoners is 1 minus this, so it comes to 0.354365, or roughly 35.5%. So that's quite amazing. If they just had no plan at all, as we saw, the probability was almost 0. And if we did this for 100, this probability doesn't change very much. It goes down a little bit here, but the probability without any strategy when you have 100 prisoners is negligible. It's not going to happen. And even more amazing is you can extend the puzzle to 2n prisoners, where n could be 5 billion, whatever, however large a number you want, and then they're given half that number of tries, and we use the same cycling strategy, and the probability converges to 1 minus the log of 2. It's basically a calculus computation. I won't do it here, but it converges. So even as n approaches infinity, using this strategy, the probability of success is still a little over 30%. It's quite amazing to me, and takes a bit to get your head around this. I've seen this puzzle a few times, and each time it becomes a little bit clearer in my head. If you want another presentation, I have a link down here for you. The riddle that seems impossible, even if you know the answer. It's a video by Veritasium. I'll put the link in the information for this video, so you don't need to copy this down here. But he goes through like a production. You know, he gets dressed up in a prisoner's suit, and he explains the probabilities, and it's quite interesting to have a look at it, you know, a different presentation. The only thing he didn't do is he didn't actually compute. He did like the first computation 1 over 100, and then he just said the other ones all follow. But there's a bit of a wrinkle to them, as I mentioned in the previous 2 slides. So I have a little bit more detail in that regard, but pretty much everything else, this video will give you more details, including the calculation of as n goes to infinity. If you're familiar with calculus, it's pretty easy to understand what he's done there. Okay, so that's the puzzle, and I hope you understood it. And if not, maybe give a try to this video, or maybe just listen to my video a second time. And feel free to put questions in the comments, and I'll try to help out if I can. In the next few slides, we're going to do some combinatoric, or counting the number of ways problems. We'll use ice cream as our example. The first problem is we have 31 flavors of ice cream, and the order does matter, and we want to stack them one above another. So we can, and you can have multiple scoops. So if you really like chocolate, you could have 3 scoops of chocolate, or you could do chocolate, strawberry, and then another chocolate, or anything you want, and the order does matter here. So you have 31 choices for the first, 31 for the second, and 31 for the top scoop, and that just gives us 31 cubed. So let's look at a variation of this in the next example. Right, this is almost the same as the last example. We have 31 flavors. The order matters, but we're not allowed to repeat. So you can only have once you pick your flavor here, the first one, then you only have 30 choices. And then you can't repeat either one of these 2, and you only have 29. So in that case, you have 31 times 30 times 29. You have a few less choices because of the restriction here of not being able to repeat. In this problem, we again have 31 flavors. However, the order doesn't matter, but we're not allowed to have repeated flavors. So you can see if we put the scoops in a dish, you can just rotate the dish around. You really don't care about the order in this case, unlike the comb, where maybe some people would like to have their favorite flavor on the bottom or whatever. So here we have no order. So the problem is just the 31 choose 3. You have your 31 flavors, and you want to choose a set of 3 from that. So we've talked about this type of problem before, and of course it doesn't have to be ice cream, but whenever you're selecting 3 sets with no particular 3 items from a set with no particular order, then you have it 31 choose 3 in this case. Now we'll next look at the case where you can have repeated flavors. So we have another example here. It's almost the same as the last, with one exception. We have the 31 flavors, different flavors again, and we want to know how many ways of putting 3 scoops in a plate where order does not matter as before, but we can now repeat flavors if we want. So there's 3 cases. The first case we already computed. That's when you are not allowed to repeat. So you have 3 different flavors, and that's 31 choose 3. Then the next case is when you have two flavors, and that's 31, choose two to pick the flavors, but keep in mind that you need to decide which two scoops are of one flavor and which is of the other flavor. So for example, if you pick chocolate and vanilla, then you could have two chocolates and one vanilla, or two vanillas and one chocolate. So you have to multiply this by 2. And then the third case is where you would just pick one flavor and you have 3 scoops of that same flavor. So that's 31, choose 1. And 31, n choose 1 in general actually is the n, and 31 choose 1 is a particular case of that. So this is just 31 as you would expect. You just pick one of the 31 flavors and you get 3 scoops of that. So you need to add all 3 of these together to get the total number for the question asked here. We have the sweater puzzle here. I've seen this in different forms. It doesn't have to be sweaters, of course, but the idea is you have a group of people, in this case 1,000, and out of the group, 995 have a blue sweater, 990 have a green sweater, 985 have a red sweater, 980 have a black sweater, and 975 have a white sweater. And the problem is to determine the least number of people in the group that have sweaters of all 5 of the noted colors. So what's the minimum number such that of people that have all blue, green, red, black, and a white sweater? So let's compute that, and if you want to try it yourself, you can pause here. Otherwise, I'm going to give you the answer on the next couple of slides. We can break the solution of this puzzle into pieces here. Let's do it first by just comparing the blue and green. Let's say that's the only 2 sweaters we had. And we can draw a chart here down on the, use the pointer. So we have 1,000 people, and then if 995 have a blue sweater, we can draw it in here, and then 990 have a green sweater. We can kind of push these 2 rectangles apart as much as we can in order to kind of see what's the overlap that would give us the largest number, the minimum number, I should say, that have to have both. So if you think about it, if more than 10 of the blue sweater people don't have a green sweater, then again, we're coming from the same group of 1,000 people. So if more than 10 don't have a green sweater from this group, then that means there's no way that you could have 999 green sweaters, people that have green sweaters. So that's the most that could happen there. And then if more than 5 people from the greens that have green sweaters don't have blue sweaters, then again, you would have to cut into the 995. So either way, the least number of people that have both is either 995 minus 10, this here, subtracting 10 from this, or 990 minus 5, and you get 285. So just looking at the just 2 sweater problem, the minimum number of people that need to have both in order to fulfill the requirements of having 995 people with blue sweaters and 990 with green sweaters is 985. At least 985 have to have both blue and green. Now what you do, the problem is just recursive from this point. I'll summarize it on the next slide. I won't draw this figure again, but what you can do is just say we have a group called the blue-green sweater people that have 985 people in that group, and then compare that to the next color sweater, and then make that another group of 3, and then compare that to the next color, and we keep eliminating more people as we go through the process. So let's look at that quickly on the next slide. So the way we solve the rest of the puzzle is we take the blue people that have both blue and green sweaters, and we make that a single group. So we combine these two. Sorry for the small type, but I wanted to fit in the problem here, or at least the parameters of the problem here, so you can refer back to it without shifting earlier in the video. So these first 2 are now a group is one group, and as we compute it, that had 985 people, and we compare that to the number of people that have red sweaters, and we say how many at least how many people need to have both. And we do the same type of analysis, and we end up subtracting the 985 from 1,000, and then we subtract that 15 from the 985, and we get 970 people. If you need to, you might want to redraw the figure I have from the previous slide and just substitute in a group that's blue/green and compare that to the group with 985, the red sweaters. So we get at least 970 people that have blue, green, and red. And you can see what we're going to do next. We'll create this as one group. These top three is one group that has 970 people. And then we say how many people need to have a black sweater compared to this group that owns blue, green, and red sweaters, which has 970 people. And we subtract the 970 from 1,000, and we get 30, and then we subtract 30 from the 980, and we get 950. So 950 people have to have, at least 950 people have to have blue, green, red, and black sweaters. And finally, we compare this group of four, the group of people that has all four types of the first four, these sweaters here, and then we compare that to those who have white sweaters. So we subtract the 950 from 1,000, we get 50, and then we subtract 50 from the 975, and we come to the final answer. So that 925 people have sweaters of all five colors, or should I say at least 925 people have sweaters of all five colors. So that's the solution. There's another way of doing this, and it's a lot easier actually. I'll explain it in the next slide. So we have an alternate solution to our problem. Another approach is to determine the number not having each color of a sweater and then subtract the sum of these numbers from 1,000 to get the solution. So it's pretty easy. We have 5 people don't have blue sweaters. I'm just subtracting from 1,000. 10 don't have green, 15 don't have red sweaters, 20 don't have black, and 25 do not have a white sweater. So these are the number of people out of the 1,000 that don't have each of the 5 different types of sweaters. So in total, there's 75 people who are lacking at least one sweater of a particular color. We add all these together. So worst case is there's no overlap between these groups of people that don't have at least one type of the sweater, and thus the 1,000 minus 75, 925, have sweaters of all 5 colors. In other words, these are the people that don't fit into any of these 5 groups here. So that's a much easier way of doing the problem, in my opinion. We have another puzzle here. I'm going to call it the bridge puzzle. We have 4 people, Abe, Beth, Carol, Don. We'll just call them A, B, and C when we get to the solution. And they're on one side of a bridge, and they need to cross this rickety bridge. And for some reason, there's a time limit on it, as well as these other conditions here. So only 2 people at a time can cross the bridge because it's very flimsy, and otherwise it'll break. It's also very dark, and it would be dangerous to try to cross without lighting your path. And so there's one lantern that between the 4 of them that they have, and that's needed for each crossing, either going to the other side or coming back to the original side. And because of the how treacherous it is to cross in the dark, the 2 people crossing pretty much need to cross together. So if you send a slow person with a fast person, the crossing is going to be constrained by the speed of the slower person. That's the reasoning for the second requirement here. Then all 4 people must be on the other side of the bridge in 17 minutes or less. So there's some impending doom on one side of the bridge, and they want to get to the other side, and maybe they're being chased by some marauders, and they want to get over to the other side of the bridge in 17 minutes or less, and then they'll cut the bridge. And it's a string rope type bridge, and they'll cut that and let it fall so that the people chasing them can't catch up to them. And we have the following crossing times. 1 minute for Abe, so he's the fastest, then 2 minutes for Beth, 5 minutes for Carol, and then 10 minutes for Don. So these are how long it takes for each of these 4 people to go from one side to the other, and also coming back if they need to. So we want to determine a strategy to get all 4 people across the bridge in less than 17 minutes or less. And just keep in mind that we can only cross 2 at a time. So, for example, if Abe and Don cross, that it's going to take 10 minutes for the 2 of them to cross together. And Abe could run back or go back in 1 minute to the other side with the lantern, which is required for a crossing. And then he could take Carol. It would take 5 minutes to get the 2 of them across. Then he could run back again and go and get Beth, and the 2 of them together would go back in 2 minutes together, since Beth is slower than Abe. But that would be much more than 17 minutes. So the question is, how do we make some arrangement to get them all, if possible? It may be impossible, but I won't tell you that whether it's possible or not here. But if there is an arrangement, then fine, and if not, prove that it's impossible. So that's the problem. It turns out it is possible to get everyone across in 17 minutes following the rules that were stated. So there's a trick at the beginning of this, which I didn't catch, but I looked at the solution. So if you didn't figure it out, don't feel bad. It's kind of tricky. So the first thing, as you might expect, is A and B cross, and that takes 2 minutes. And of course they have the lantern, that's the condition. So the 2 of them cross. A leaves B on the other side, and A goes back, and that takes 1 minute. So we're up to 3 minutes here. Now here's the tricky part. You actually let the 2 slowest folks go across now. So D takes 10 minutes and C takes 5, so they're constrained by the slowest of the 2. So it takes 10 minutes. Of course, they're carrying the lantern. And then because B was left on the other side, it's only going to take Beth 2 minutes to come back. So we've got 3 minutes, 13, it's 15 minutes. And then A and B, being the 2 fastest, they're only constrained by the time of B, and that takes 2 minutes. So 17 minutes, 2 plus 1 plus 10, and the last 2 trips take 2, and everybody's across, and they cut the rope, and they're all safe. So this comes in a class of problems that I wrote about in one of my puzzle books. I'll put the link down there and give you the reference. That there's various conditions as to when this is possible, and when you would take this approach where you use the 2 slowest crossers at the same time. That's not always the best solution. So there's a more general problem, and again, I'll point you to some discussion on that in a book that I've written, and it's free to download, so it won't cost you anything to have a look at that.